Hello and welcome to SUNY Plattsburgh's The Mathematics of Juggling. Specifically, we'll be talking about something called site swap juggling, a highly restrictive but mathematically based form of juggling, not juggling as an abstract concept. Site swap juggling is represented by an infinite repeated pattern of whole numbers, such as this pattern, which consists entirely of repeated threes. The places in the pattern represents which hand is throwing the item, and in site swap juggling, this will always alternate. The item is first being thrown from the left hand, and then the second item is being thrown from the right hand, then the left, and then the right, and so on. Now, the numbers in those places represent how far the object is being thrown and where it is landing. The 3 that begins this set, for example, represents that the item is being thrown 3 spaces later on into the pattern. The second 3 is a new item because nothing is landing in that hand, and it's also thrown 3 spaces later on. The third 3, yet a new item because nothing is landing in that hand, is also thrown 3 spaces later on. In the fourth spot, we see that the first item has been caught, where it will be thrown 3 spaces later on. Then the second item is caught and thrown, the third item is caught and thrown, the first item is recaught again, and so forth and so on. This is what this example would look like. Notice that the red item is being thrown first, then the blue, then the green. Back to the red, back to the blue, back to the green. This pattern lasts indefinitely with no reason for it to stop, which is why this pattern is called stable. Now we can do exactly the same thing by replacing all of the 3s with 4s, but if we do that, the pattern does not look the same at all. It is stable, but it clearly doesn't look the same. That's because of what the places stand for. Remember, the places stand for alternating left, right, left, right. 4, being an even number, will always land in the same hand in which it was thrown. 3, being an odd number, will always switch hands every time. From that information, you should have a pretty good idea what this infinite pattern of 5s is going to look like. As you can see, they keep switching hands. 5 is an odd number, it will always land in the opposite hand from which it is thrown. And again, this pattern is also stable. We can continue this forever with no deviations. Now, we don't have to go up, we can go down. A pattern of infinite 2s is also a stable pattern, but the same item just keeps getting bobbled up and down in the same hand. It's stable, but it's not terribly exciting. An infinite string of 1s is also stable and also not very interesting. As you can see, it is simply the same item being thrown back and forth between the two hands with no other items getting involved. So how can you tell if a pattern is stable? Well, you're really looking for 2 things at once, and it does sometimes require you to actually draw it out. In this case, for example, the first item, the 5, gets moved 5 spaces down the line where it lands on that 1, where it moves 1 space down the line it becomes that 5, where it moves 5 spaces down the line it becomes a 1, and so forth. The following 3, a new item, because nothing is landing in that space, gets moved 3 spaces down where it becomes a 3, where it moves 3 spaces down it becomes a 3, and so on. The third item must be new because nothing is landing in that hand. The 1 moves next into the 5, where it moves 5 spaces down the line and it lands in an empty 1, where it lands 1 space later and lands in an empty 5, and that goes on forever. With this, we have filled every single spot in the pattern, and also we have not had 2 items land in the same hand at the same time. Infinitely repeating 5, 7, using exactly the same principles, also turns out to be stable, and it ends up looking like this when we're finished. And meanwhile, the alternating pattern 1, 5 also turns out to be stable, and it looks like this nearly circular pattern. But it doesn't always work out, such as with this pattern of infinitely repeating 1, 4s. While it looks like it's holding on for a while, it eventually comes to a crashing halt. As you can see with this freeze frame here, the red item and the green item are about to land in the same hand at the same time. That is an unstable pattern, and it gets a lot worse. If this pattern is forced to continue, you see an infinite number of new different color items being thrown from the left hand into the right, and nothing is landing in the left hand at all. So what causes this pattern to be unstable? Well, the first item, The 1 is thrown immediately into the 4, where it's thrown 4 spaces later to become a 4, where it's thrown 4 spaces later to become a 4, and so forth. The second item, which appears at that second 1, something is landing in the first 4, that is not a new item, but that one gets thrown into a 4, which gets thrown 4 spaces down, which gets thrown 4 spaces down. So far, so good. It is when the third item appears that we have a serious problem. It immediately gets thrown 1 space into where the first item is landing. That's 2 items landing at the same hand at the same time. That is an unstable pattern. And the problem only gets worse from there. The next one is a blank spot. Nothing is landing there. It must be a new item, which means that it too is not only landing in the same hand as something else, but the one that follows will be another item, and the one that follows will be another item, causing you to have an infinite number of thrown and caught items. That's impossible. That's unstable. Once a pattern has any collisions at all, the pattern is completely broken, it's unstable, it cannot be fixed, as it always ends with an infinite number of items, and there's nothing that can make that possible, or therefore useful. Based on the way the pattern is set up, some patterns will take longer than others to display whether or not they are unstable. But unstable always means the same 2 things happening at the same time. 2 items landing in the same hand at the same time, and therefore an infinite number of new items basically appearing from nowhere. So we found some patterns that are stable, and we found some patterns that are unstable. As it turns out, whether or not a pattern has any chance of being stable is actually pretty easy to detect once you know where to look for it. So I'm going to ask you to pause this video right now, look over the examples as we've seen so far, and see if you can figure out what is the restriction that a pattern must have in order for it to be called stable. Go ahead and pause the video. So take a look at these 3 patterns. You'll notice that the average of each of them is a whole number. More importantly, that whole number average is also the number of items that are being thrown and caught in the stable pattern. Go back and take a look at the video if you want to check that. By contrast, if the average of the numbers in the pattern is not a whole number, it has no chance whatsoever. It cannot be fixed, it cannot be made stable, even by rearranging its entries. So with everything we've seen so far today, here are 4 more infinitely repeating patterns. Take the methods that we've looked at and try to find out which, if any, of these patterns are stable and which are unstable. Once again, go ahead and pause the video while you work that out. Okay, so let's go over the answers. Done correctly, A and B should have turned out to be stable, while C and D should not. Now, D had no chance whatsoever. The average of the numbers in the pattern was not a whole number. But for C, it was. B and C both had the same average, 4, but B worked and C did not. To make this absolutely clear, what that means is the average must be a whole number in order for it to have a chance of succeeding, but you might have to rearrange the terms in order for it to actually work. If the average is not a whole number, it cannot be saved even by rearranging the terms. So there we go. That is a quick look into the mathematics of site swap juggling. Because it involves moving objects, it makes sense that it isn't in the textbook. So I'm going to ask you instead, as practice problems, to try to come up with 2 more stable and 2 more unstable patterns. You may even make them accidentally while trying for the other ones. Thank you and have a good day. This video is the sole proprietary. This is a SUNY Plattsburgh video. Hey, we can edit that out in post, right?